All right, so let's get started with lecture 21, which is approximation. So the idea of approximation, well, let's just kind of look at this for a second. So we're going to talk about why we do approximation, and then how we do that. And we're going to look first at given we're approximating, we're not going to get exact results. So we're going to look at what we're going to use to try and judge whether we have good or bad results as far as our approximation function. We'll look at, we're going to start with linear methods, although we will eventually go to some other types of methods for approximation. And we're going to be looking, starting today, at stochastic gradient descent. So why approximation? Shannon. So give me some reasons why we would need to have an approximation of our value function.
Tabular methods, sorry, mic might be bad. The tabular methods rely on you being able to enumerate all of the state action pairs. So if you have a really large state space or a really large action space, that's not going to be feasible.
Yeah, so we have to enumerate all of, depending on whether we're doing state values or action values, we have to enumerate all the either state value combinations or state action value combinations, right? And if it's too large, as you say, then we're not going to be able to do that. Now, when we talk about too large, what is too large? Back to you, Shannon. Or give me an example of too large.
It depends on how good your computer is, but like chess or Go or both.
And I see you're not muted, but I'm not hearing you.
Are you hearing me now?
But you can, Varun, you hear her, and I don't hear her. Very interesting, because I heard you first. Can someone else say something?
Testing.
Oh, I heard that. It was extremely quiet. Say it again, Garrett.
Testing.
All right.
Test.
Let me try
Test.
Oh. Speak again, someone. Oh,
Hi, Prof. Rhodes.
Oh my goodness. Well, I turned up the volume all the way. Thank you very much, Dave. Okay, so I had a cable that wasn't fully plugged in, so it was sometimes working. So Shannon, go ahead. What's too large?
Too large depends on how good and like how fast your computer is, but traditionally games like chess or Go have both been too large to like fully enumerate.
Yeah, and why is speed a problem for enumeration? Because I would think more memory is the problem.
That's true. I guess in terms of enumerating the space, that would maybe be more memory intensive, but then just being able to like locate the space you're looking at.
So we got two problems. We have the memory issue, which is storing the table. And then we also have the, let's say, CPU issue as far as, let's say, filling in the table, right? And those actually are two interesting points, okay? So, so a good example would, you're right, be, let's say, chess, where we have lots of different states, okay? Although a finite number. Can you give me an example where we might have an infinite? We would need an infinite table in order to store our values. Let's switch to Dave.
Sorry, did you say my name?
I did, yeah. So my question is, so we got now, for instance, for chess or Go, is we have so many different states that it's not practical, right? You know, more than there are atoms in the universe, let's say. But can you come up with an example of a state space or a state action space where we actually have an infinite number of states or state action pairs?
Does it have to be a game, or could it
Doesn't
be
have
like,
to be a game, no.
Like, let's say, like if you're doing self-driving cars or something, that environment is infinite.
What about a self-driving car is infinite?
The states that well, so like then the states that it might find itself in is infinite.
Tell
Because
me examples. What sort of states does a self-driving car find itself in? What state?
for example, the exact location within a road and the direction in which it's driving in. So like,
Okay.
let's say how much the steering wheel is rotated.
Okay, so let's say rotation is an example of steering wheel, just to come up with something simple, right? If this is a real number, then we have an infinite number of possibilities. Okay, so if we had something simple like the cart pole, do you remember that one? We were trying to balance a pole on a cart, and there, one of the readouts we can get is the angle of the pole. So that's one of these elements of the state space, and that is, as long as it's a real number, infinite. So that kind of memory issue is very clear, but also then the CPU issue is of interest too. So let's say we have a huge state space, right? So we have this huge state space shown in this, 2-inch by 1-inch place. But anyway, a huge state space. And we go ahead and start filling out parts of the state space. So we know what this is, and we know what this is, and here, and here, and we're going all over, and we're doing things, right? And as long as we go, we're going to be still filling in only a very small fraction of that state space, right? If it's finite. If it's infinite, it's a really small fraction. So the question is, what happens if we now want to know what's at this particular value, right? So we've got a state that's maybe close to another state we've seen before, but is not the exact same state. And so we want approximation for two things, right? We need to approximate in order to be able to represent all of the states and values that we've seen so far in some sort of approximate function. But more importantly, we also want to generalize. So we want to generalize to states or state action pairs that we have never seen before, based on the values that we have seen. That is similar to, let's say, a prediction problem where right, so let's say we have a much simpler problem, right? So we have a regression problem. We have some x's and we have some y's, and we have some particular samples that we see over time. So we see these samples, right? Maybe this is, I don't know, height is our x-axis, and this is weight is our y-axis. Particularly, I don't particularly care what they are, right? So we've got some sort of values that we have, actual values that we have, and now we want to know, let's say, for this particular height, we want to know what would be a good estimate of the weight. And I'm guessing, right, about that height that I go with green would be a good estimate. We've never had any samples for that particular height, but we assume that we can generalize from the heights we've seen so far and their associated weights. And maybe what we have is we could come up with some sort of a model or an approximation. Maybe our approximation is going to be something like this, right? So this is approximate. This is a linear approximation, and we do see that we have some errors, right? If we look at the rightmost red, we have an error between here and here, right? So our approximation function is not exact. And we have an error here, and an error here, and an error here. And we have one where we have zero error, right? Zero error. So by having this linear approximation, we're saving space, for one thing. Okay, if we had a tabular method, if we've had 1, 2, 3, 4, 5 samples, then we've got to keep track of a table with 5 entries in it. 1, 2, 3, 4, and 5, right? With our X and Y values. Nick, if we have a linear approximation, how much information do we have to save?
Just the slope and the intercept.
Yeah, we'll have to save slope and intercept. Right. So we're going to call these our parameters, or we might also call them weights. So we've saved space, and we also are able to generalize. Now, there are other ways we could generalize. We don't have to use a linear function, right? We could say, well, the way I'm going to generalize is I'm going to say, let's say if we want to have this green guy, let me redo. I'll redo this chart right up here. So we have here and here and here and here and there, right? So we might say it's roughly the same numbers. So now if we want to say I'm at this X here and I want to know approximately what its value is, an alternate I could say is, well, what's the nearest neighbor, right? What is the closest one that I have seen? And it's, let's say, this guy. And then just use its value. Okay? Or maybe 2 near ones and take an interpolation. So there are other ways in which one can do function approximation besides, let's say, linear or polynomial, or as we'll see later on, neural networks. So a much different approach is to just save exemplars, so to speak, just save particular ones. And as long as we have a notion of distance, then we can go ahead and assume roughly that if your X is close to an X you've seen so far, then the associated Y will be similar. Questions so far? Okay, so our value function is going to take a state, and it's going to take some weight vector, right? These are just, for the linear case, this is a weight vector of size 2, right? We'll have a slope and we'll have an intercept. If we had, and we can represent kind of whatever we need to as far as those weights. We might have a decision tree, for example, where we'll say something like, you know, if X is less than 5, then go one way in our tree, otherwise, you know, go another way, and then have other sorts of checks that we make on other various parts of the state until we eventually get down to some leaf that says the value equals, you know, 3, and some other set of decisions that we can make. And here we might get a value equals 6, and so on. And so we just have a bunch of decisions that we look at represented in a tree. Well, we could represent that with a weight vector as well by somehow representing what our cutoffs are and what parts or features of the state that we're looking at. And also then what the associated values are. That could be represented in some very large weight vector. So having a weight vector, even if we don't actually use it for weights, just think of it as a parameter vector, is general enough that we can do whatever we might want to do as far as function approximation. Okay, so our approximate function, value function, basically takes a state and then takes our weights. And these are often going to be learned weights in some way. And this gives us our approximator, right? So we've got our true v sub pi and our approximation, which is v hat. Does it make sense? Any questions on that? Okay. What we have been doing is we have been updating, let's say v of s, right? Or q as well, where we say v of s equals vs plus some alpha times r plus some, let's say, v of s prime minus v of s. And in general, to be more general, this is some target minus V of S, where V of S is our current value, and this is our target value, and we move it a little of the way, right? So we move it part of the way from our current value to our target value. So we've now got sort of two sources of error approximation here, right? One is if we've got this bootstrapping method, V of S is has been calculated based on bootstrapping and based on samples, right? So we'll eventually converge to a true value, but we don't have a true value right now. The other problem is our current value, we don't have direct access to, right? Our current value is actually an approximation from V hat, okay? So what we'll be doing is we will be calculating a new target. And if we're using bootstrapping, this may be using V hat rather than V sub pi, right? So we have a source of error there because we don't actually know what our current estimate is exactly. We know an approximation of our current estimate. And then we'll go ahead and figure out what our target is. And then we will update. Well, what are we going to update? So let's think about this a second. We have an approximation function, and we want to change the approximation function in some way, right? Because we want to update V hat of S comma W, because we want it to be more towards the target than it used to be. So Sina, what is it we can change about V hat of S comma W to make it have a new value for us?
Sorry, could you repeat the question?
Yeah, so the question is, we have a current value, V hat S comma W, okay? And now we want to update S's value, so we go towards U, okay? So we want to modify V hat of S to W, so we want to make it more towards U from what it used to be. And the question is, what can we change about V hat to make its evaluation be different?
You could change the weight vector.
Yep, that's all you can change, right? You're not going to change how we've defined V hat. All you can change about it is the weight vector. And so that is what we're going to be doing. We're going to be updating the weight vector over time, right? So presumably, if we want to change the weight vector for V hat to be more towards U, we hope we can make that change to W to make that happen. But what's it going to do to other values, other states?
It's going to change those. If you
It's going to change those too. Yep. Maybe better, maybe worse, right? Our goal is going to try and be such that as we make these changes, overall, we're getting things better and better. All right? Does that make sense? So we're having to do these updates, right? We are normally doing these updates, let's say for TD, where we are updating our V function. And as part of doing these updates, what that's going to mean is we're going to actually be updating our weight vector. And the updating our weight vector may be or will be making some changes to other states. And we just kind of got to balance this all out and make it work. So we need some sort of an objective function, some sort of a way to say how well are we doing, okay? How good are we doing overall in terms of our approximation? And the simplest thing to do would be some mean squared error. And so that's what we'll do. So if we look, again, at this case, if we imagined we were in this two-dimensional world, right, where we had, let's say, S here, and we had v prime of s on the y-axis, and then we have a bunch of samples. Okay, like that. And if our v hat were a linear function, so let's say, I don't know, this is v hat. Okay, and it's really v hat with a particular set of weights, right? So it's a particular intercept and a particular slope. Okay. So if we look at this, is this as best as we could do, Sina, in terms of approximating those red v primes or v pi's?
Did you say, is this the best we can do?
Yeah, is this the best we
No.
could do? Now, what might you change about the slope?
You might increase it.
And what about the intercept?
The intercept maybe could go up a little bit too.
Yeah, I'd say, you know, let's maybe something like that. Maybe. Maybe it has to go up a little more. But this is certainly better, right? It's better than the blue. Okay. And so the way we'll measure this is we'll just go ahead and measure the sum of the squared errors. Okay. So that's our sum of the squared errors here. And we can see our term here is really our true v sub pi, where by true, what I mean is, well, actually, let's look at that as, yeah, as our v sub pi, because that is eventually what we want, is our actual value for that state with a given policy. And then our approximation v hat. So we'll take the sum of squared errors and we'll go ahead and weight it, because maybe, you know, this state is very unlikely. And this state is very common. So it makes sense to go ahead and weight the errors based on how likely you are to actually see that state. Right? And so that's what our mu here is going to be. Our mu is basically just a distribution function that tells us how likely we are to be in a particular state. Okay, make sense? Any questions at this point? Okay, so how do we know how likely it is to be in a state? Often what we'll do is just look at how often we're in that state as we carry out particular episodic tasks. So if we look at policy pi and we then say how, one second. Okay, so let's say we need to first know the probability of starting in a particular state. So it'll be some h of s here. And then how long are we in a particular state? So this is, you know, eta of s is going to be, well, what's the probability of starting in that state? And then what is the probability of being in a predecessor state? Okay, times the probability of going from that predecessor state to a new state. And that's a probability based both on the environment and based on the policy, right? So basically, if we're in state S bar, what's the probability of taking a particular action and then that action leading to probability S? And once we've done that, all that, we can kind of normalize so that this turns into a, so that they sum to 1. Okay, this is not unlike the original PageRank algorithm for Google, where we looked at sort of what is the probability of going from one particular web page to another particular page. So that was based on the links on that first page. And then what's the probability of being in a particular page? So looking at this, a link as basically being a way of getting from one page to another page. And PageRank, basically says how popular is a page. It's what's the likelihood that if you just randomly surfed, you would end up on it. Okay, and so yeah. Anyway, okay. So does this on policy distribution make sense? So if you were looking at something like chess, you might have bunches and bunches of states, the possible state space, that have very unlikely probabilities. Okay.
Prof. Rhodes, I have a quick question.
Sure.
So in order to have this sort of, it kind of looks like the environment function with like the SRSA that we'd had before. But does this require us to either like definitely have a model or also be building some sort of distributional model along the way? Or is there some way that we can, approximate that value as well, that function?
Well, we can certainly approximate this function. And the way we can approximate this function is just keep track of how often we end up in a particular state, right? We might have to create an approximation function for that too, though, right? Because of the fact that the state space might be infinite.
Got you.
Yeah, but we could just keep account. Okay, so we have this error function, right? So this is our value error function. And I may sometimes call this a loss function. So the loss function just tells us, how bad we are, or how good we are. No, it's how bad we are, because a bigger loss means we're worse. So our goal would be to find some W star, right? Some set of weights such that it has an error no worse than that of any other set of weights. Do you agree that's a reasonable goal for our function approximator? Give me, let's say, a thumbs up for that. Okay, at least I got one. Good. All right. But that's not necessarily possible, right? Because the way we are searching our weight space, it may be that so if we use gradient descent, the idea there is conceptually, let's say this is sort of our weight space here, and this is our error here. So weight versus error, and our goal would be to end up, Garrett, where on this sort of map?
The global minimum on the right side.
Yeah, so this is where we want. This is our W star. But the fact is, the way we may be traversing through this is we may be, let's say, starting here, and then we're going to do gradient descent, which is basically the opposite of what you might say is hill climbing. It's another thing. So hill climbing is when you get to the top of hills. Gradient descent is when you want to get to a valley. So we may start taking small steps until we can no longer go down, and we would end up somewhere here. So we would end up at this local minimum where in the neighborhood of where we're at, we're less. Our value function, our loss function is less. Even though there may be somewhere sort of outside of our neighborhood where we've been less than that. All right. We'll talk about briefly sort of about neural networks and the fact that just it sort of turns out that they would do a pretty good job of finding minima that are not that far off from the global minimum. But for right now, we're not talking about neural nets. We're just talking about this idea of having a loss function based on weights and changing those weights to reduce the loss function. Okay. And this uses the idea of the gradient. So a gradient is really an operation that applies to a function and that returns a vector of functions. Okay, so if we have, so let's look first just at a review of partial derivatives, right? So if we've got, let's say, f of x comma y equals 2xy, and we want to know the partial derivative of f with respect to x, that basically says, let's just treat all the other variables or parameters to this function as constants. Okay? So therefore, when we're taking the derivative of f with respect to x, we're saying y is a constant. So if y is a constant and 2 is a constant, then Jake, what is the derivative of 2xy with respect to x?
2y.
2y, right? So 2 is a constant, y is a constant. We just leave the constants alone as we're doing the derivatives. And away we go. Okay. And similarly, the partial derivative of f with respect to y is equal to 2x. So the gradient takes a function of, so let's look at, instead of f taking xy, let's say f takes w, which is some vector. Okay, let's say a vector of 2 elements. Okay, and it equals 2 w0 times w1. All right. So if we call f of, let's say the vector, and I'm going to use column vectors almost all the time here. So if I pass in the column vector 2, 3, then this equals 2 times 2 times 3, which equals 12, right? Okay. So the gradient, and the name of this operator, does anyone know the name of this operator?
Laplacian?
The what?
No, never mind. Never mind. I was saying Laplacian, but I think that's...
Yeah. It's, let's see if I get this right. I believe it's Nabla is its original name, but more often, and so if you use LaTeX, that's what it uses, del. So del f of w. So anyway, if we have our particular f here, which is 2w0, w1, then this would be the partial derivative of f of w with respect to w0. And I'm being inconsistent here, and I apologize, so I'm using w0 and w1. Let me just switch over to use w1 and w2. Okay, so this is the derivative with respect to w0 and the derivative with respect to, sorry, w1 and w2. And so this equals, Sean, what's the derivative of f of w with respect to f1? Sorry, with respect to w1.
Can you hear me now?
I hear you now.
F of w with respect to f1.
Sorry, w1 with respect to w1. So we're looking at this function here and taking the derivative with respect to w1.
It'd be just 2w2.
Yep, and the next one. So with respect to w2.
2w1.
Yep. So the del operator, or the gradient operator, has taken a function, right? We've applied it to f, and it has now given us a vector. So f takes a vector with of size 2, of length 2, and it returns us then a vector of length 2 whose values are themselves partial derivatives, which are functions. Okay. Why do we care about this? Well, let's say we are on the top of a mountain. Okay, so we have gone hiking. We're on this mountain. It's now dark, and we want to get down. right? Dark, it's like really dark, pitch dark. So we want to figure out how to go down. Let's see. McKenna, how would we figure out how to go down?
Well, if you start going in one direction on the function, you'll see if the output is going up or
Yeah,
down.
okay, so that's mathematical, and I agree with that. So let's say we're actually on a mountain, okay? And it is pitch dark. How do you know which way's down?
Gravity.
Okay, so how would you use gravity? Let's say you had stuff in your pockets if you need to, you know, whatever you might have planned ahead.
Sure. Say you have a ball.
Okay,
Put
yeah.
it on the ground and then it will roll down.
I like it. So you brought a ball with you. That was very, very foresightful. And then you start following the ball, right? The ball will start rolling down the hill because that's what balls do. They roll downhill. Okay? And in two dimensions, right? You have, let's say, something like this, and you are up on the mountain over, let's say, here, and it'll start rolling down to the right. Okay, but in 3 dimensions, the ball might roll a combination of, let's say, north-south and east-west, right? So it'll have a north-south component to its movement and an east-west component to its movement. So we could talk about the fact that a location, right, has an X and a Y component. So we have a vector with an X and a Y. We can talk about the height of our location. And we can talk about the del of our height, right? If we look at del of our height, which is our gradient, that's going to basically tell us what is the partial derivative of the location with respect to X and the partial derivative of the location with respect to Y. So let's look at these numbers, right? Let's say for a particular location, our gradient is 5, -3. So back to you, McKenna. Now we're back in math land, of course, right? So what does this tell us about our ball? What is our ball doing at this location? Like, which direction is it going?
That means that in the X, it's moving to the right because we have 5, and then in the Y direction, it's going down. So we've gone to the right on that hill.
Almost. Here's one thing you have to be aware of, and that is this gradient is telling us that if we increase X a little bit, right? For every unit increase of X, our height increases by 5. Increases, right? So this says if X goes up, that implies that our position goes up, right? Because when we look at the derivative, that's the slope, right? And the slope tells us where to go up. And if Y goes up, what happens to our position?
The position goes down.
Its position goes down, that's right. So since we are not trying to climb the hill, we are trying to go down. Or another way to think of it is, since the ball is going down and not up, right? It's going with gravity instead of against gravity. That tells us that our ball is moving down in the x-axis and up in the y-axis. Does that make sense?
Yeah.
It makes sense why it's backwards, because
Yeah.
we're doing descent rather than ascent. Okay, so that's the reason we calculate gradients. We calculate gradients in order to tell us the derivative with respect to what we're going to end up with is with respect to each of our weights. And then we're going to say, don't go in that direction, go in the exact opposite direction, right? Because our gradient is going to tell us how to increase our loss with every component of our weight, right? If we change this weight in this direction, it will increase the loss. This weight in this direction will increase the loss. This weight in this direction will increase the loss. And we'll say, okay, go in the opposite direction. And also it's giving us not just a direction, but also a magnitude, right? So it'll say, for instance, in this example we have here, that changes in X will change our loss or our height more than changes in Y. Okay, any questions on this? Okay, so here's what we're going to do. We've got our loss function. Let me actually make it slightly simpler. So stochastic gradient descent. And then we also have versus, let's just call it gradient descent. Okay. So in gradient descent, we have a set S of states, and we have their associated v sub pi's. Okay, and so we can go ahead and calculate, as we looked at before, our loss. So we could just go ahead and calculate that loss, right? I'm gonna make it easier, and let's just assume for a moment that these are equal probable. Okay, so if that's the case, this is really going to turn into 1 over the size of S times then the summation of S in capital S of our loss. Okay, so that will be our loss. So this we can say is dE of W equals that. Okay. So if we look at the gradient of VE of W, what, Julius, does that measure? So this measures what?
The gradient, the gradient of VE.
So yeah, it's the gradient of VE. What are we trying to do to VE? Increase it or decrease it?
So it's a loss function, so we want to decrease the loss, right?
We want to decrease it, that's right. And we have the gradient. So the gradient is going to tell us for each component of W how to increase the loss, right?
Wait, so increase the loss or decrease?
Well, it'll tell, the gradient tells us to increase. If we want to decrease, we'll just put a minus sign.
Okay.
Right? So knowing how to increase, it's very easy to know how to decrease as well. So therefore, what we're going to do is, so I'm ignoring 1 and 2 right now, okay? And I'm actually ignoring 3 in terms of the individual loss. I'm just talking about the total loss. So we can actually calculate what this is. All right, so let's look at the derivative of this. Sorry, the gradient of this. So we're going to need a new slide here. Let me make some more while I'm at it. Okay, so we have that VE of W equals 1 over the number of samples. This is just so we're doing an average, right? So this is going to be the average mean squared error Sorry, it's just not writing. Average mean squared error. And then the summation for S in capital S of, and we're taking what? We're taking the hat of, just make sure I get this right. We'll take the order I do this shouldn't really matter since we're squaring it, but nonetheless. So v pi of S, that is the actual value function for this state, minus our approximation. So do I put W or S first? I'm putting S first. Okay. Now let's look at the partial derivative with respect to the ith W, right? The ith weight. Let's see. So we've got this summation. So we know that we can just sum together the derivatives, right? So we can actually take the partial derivative of v pi of S minus v hat of S comma W squared over the ith weight. And this equals, so now if we take the derivative of this, we can just use the chain rule, right? This is 2 times v pi of S minus v hat of S comma W. Garrett, what else do we need for our derivative?
I'm not sure.
So we're taking the derivative with respect to W, right? So we had, you know, this is, see if I can. So we have here, we're taking the derivative of this something squared, right? And so it's 2 times that something times the derivative of the something. So we need to take the derivative of what's in this brackets with respect to W sub I.
So then it would only be a function of the second part because the first part doesn't depend on W?
Exactly. The first part doesn't depend on W, so that's going to be 0. And so it's just the derivative of the second part. Right? So we'll multiply by the partial derivative of V hat of SW divided by W sub I.
Wouldn't it also be negative?
Yes, it would. Thank you. So I'm just trying to decide where to put the negative. I'll put the negative outside, right? It's one little application of the chain rule. Okay. Yep. Okay. So let's look at this. So this equals 1 over 2 times, I'm going to pull the negative back out and switch the orders of these, times the derivative of V hat. So here's where it actually matters how we're representing V hat, right? Because that'll tell us what this derivative is. The other thing to keep in mind, though, here is, so we basically got this value multiplied by the derivative of V hat with respect to WI. If we looked at the gradient of VE, that's just going to be equal to a bunch of elements of a vector, all of this form. Okay? They're all going to have the same value before the partial derivative. Okay, that same term of 1 over the cardinality of S times the summation, blah, blah, blah. Okay, so we can pull this out and just say this is going to be 1 over S times the summation of S in S times 2 times V hat SW minus V pi of S, and multiply that all times what's going to end up as a vector of V hat derivatives. Well, a vector of V hat derivatives is just the gradient of V hat. So what we're saying is the gradient of the loss is going to be this term here times the gradient of the approximate value function. Okay, questions on that? So let's look at it with some given particulars. So we can reduce the loss by adjusting W in the opposite direction of the gradient. Okay, so let's look at that a moment. We're saying that what we can do is, so we're going to take the weights. We've got existing weights, and we want to move the weights. We've got a gradient. How far do we want to go? So let's say we have, in this two-dimensional case, and we're here, okay? So our gradient tells us what direction is up. We want to go down, but how far do we want to go? Dave?
Well, probably want to take little steps so that you don't overshoot it.
That sounds perfect to me. Take little steps so we don't overshoot it. So we are going to use this alpha parameter here, which will tell us how much to move, and we'll basically take baby steps. Because if we take huge steps, then we could say, okay, we know we want to go to the right, so we will go from here, is our current value of W. We'll just go, we'll take a big giant step and we'll go to here, okay? And we've actually ended up now going up a little bit, right? And skipping a lot of hills and valleys and so on. But by taking such a huge step, it's as if we had our ball up at the top of the hill, we watched which direction it was rolling, and then we just, ran for an hour in that direction, up and down and up and down and up and down, and then didn't see where we landed, as opposed to maybe taking one step. Okay, because the gradient is a local measure, right? It's a measure locally of what's up and what's down, as opposed to some sort of global measure. So we are going to say that our new weight, WT sub 1, t plus 1, is going to be our old weight minus a fraction of the direction we want to move. Okay, now so let's look at this a moment. We are taking minus, and this is because we're trying to reduce the loss, right? We have a half lambda here, or a half alpha here. I'm going to talk about the half in just a moment. But we have our alpha that says baby steps. And then we have our gradient, okay? Where we've lost our 1 over, right now we've lost our average over all the states. And here we're just looking at a single state. So really just looking at the loss for a particular state, okay? I'll talk about that in a moment. So when we take the derivative, of course, the 2 comes down just as it did before, cancels out the 1/2, And that's why we had the 1/2 there in the first place. It's just because since we're doing a squared error, we know when you take the derivative, we're going to get a 2 come down. And we're going to be doing this calculation all the time. And so we don't have a 2 in here. So we'll start out with a 1/2 to begin with. Okay. So we have alpha times the difference between our prediction or our approximation minus actual. And we're going to multiply that then by our gradient of our actual approximation function. So this is a general purpose technique of doing gradient descent with any particular approximation function you want. All that's necessary is that that approximation function be differentiable. Okay. And now let's go ahead and look at it and apply it to linear case, which will make it easier.
Prof. Rhodes.
Yeah.
So just to clarify, the W that the W is a vector.
The W is a vector. Yes, it is.
So we're updating every single component of that vector with every iteration.
So yes, every time we have a new state and actual value function, we will go ahead and update this vector. And so let's make it simple. Let's say we're trying to do an approximation. We have, go back to where we had, so we have this six states and their true values, and we're trying to create an approximation function. We would go through and we could either take all 6 of those states as a whole and calculate the entire loss function and then reduce it. But since we took a small step, we're not done yet, right? So we'd have to run through them again and again and again and again and again. And over time, we will converge to our, in this case, since we have a linear function, we'll converge to the true minimum as long as our alpha is small. But yeah, we have to do it over and over again. So those weights are getting updated a lot. The calculation of the total loss. So here, calculating this, or similarly, calculating this can be expensive if we have a lot of states for which we have corresponding actual values. Okay? In fact, the whole reason we're doing this is because we have a lot of states and we don't want to save all of the state and value pairs. So instead of going ahead and calculating the total loss and taking the derivative of the total loss, what we can do is do this stochastic approach. So the stochastic approach says, sorry, let me get back to it. The stochastic gradient descent says just sample one state at a time. So instead of looking at the totality of all of the states and all of their errors and going in a direction that reduces all the errors, instead we say, let's pick one state and reduce its error, okay? And then let's pick another state and reduce its error, another state and reduce its error, and keep going over all the states that we have, and then do it again and again and again and again and again. And over time, it turns out that we will still end up in a correct descent. What may happen is we go in, we may end up sometimes increasing the loss, overall loss, and sometimes decreasing the overall loss. But over time, we will decrease the overall loss. So we just pick random states and update them. And in our case, what that's going to look like is as we're calculating new value functions for states, we'll just say, okay, feed that into the approximation function. And then as we get another one, okay, feed that into the stochastic gradient descent. And another one, feed that into the stochastic gradient descent. So we'll continually be updating the weights. Concept makes sense? So it's more accurate to be doing the gradient descent over all of the points that you are trying to reduce the loss of. But it can be expensive. And that expense means that maybe you're going to take a long time before you can figure out your first update to the weights. Whereas if you just taken a simple sample, you could quickly update the weights, and then that would be more accurate as you're going to do the next sample and next sample. So let me show you linear. A linear is a very simple model for an approximation function. So we're going to just say that we have, I'm going to say here, a feature vector of S. So we're going to extract some information from our state. Okay. What might that be? Let's say S is a chessboard. Okay. And so we might extract, let's make it a chessboard. So we might extract one feature of S, which might be, I don't know, the number of pawns. And we might so say that the second one is the number of, knights, and go on. And then maybe x11 of S might be whether we're in check or not. And x13 might be, something about our mobility, in the middle of the board. Okay, so these would all be considered handcrafted features. And this is not uncommon for machine learning, is to use knowledge about your domain to try and pick out features that you think will be useful for solving your problem. So in this case, these will be features that we hope will be useful for approximating the value of a given chess board configuration. Okay, we might consult with domain experts to try and come up with this, but these are feature vectors. Okay, so we are going to extract from a board config a set of features. So this might be, and we might keep track. So this is maybe the number of pawns for white and the number of knights for white. And this is in check white. And we might have the same thing for black and so on. So we might have 0, 5, 1, 3, 8, right? That's a particular configuration. Well, a very simple model that we're going to use for approximation for V hat is just going to be that we are going to have our features, D features. So this will be, let's say, D elements. And we'll have associated D weights. And we'll basically multiply every weight by the feature, sum them up, and we'll get our value. So we might have, let's say, let's use a simpler example where D is 3. So X might be, 3, 1, 2. And W might be 1, 2, negative 1. And in that case, V hat of, why am I saying W? So this should really be, I'm sorry, V hat of W comma S, right? Because V hat takes both a weight and a state. So this would be, oh, I'm sorry, never mind. We do have X of V hat takes a weight and a state. And in this case, we extract with X the features from S and then multiply by W. So this would equal 1, 2, -1 times 3, 1, 2. And that would equal 1 times 3 plus 2 times 1 plus -1 times 2. So that would equal 3. And so that would be our approximation for whatever our state S is that ends up with the feature vector 3, 1, 2. Okay. Questions on that? So how is this good as approximation? Or how is this good for generalization, let's say? Well, let's say we have another board configuration that has the same number of pawns and knights and so on, but a pawn is in a different configuration, right? A pawn is moved from this space to this other space. But as far as the feature vector is concerned, it's still the same, right? We don't have any feature that is different because this pawn is moved from here to here. So in that case, our approximation function would say that we have the same value for this one state and this other state whose difference is only a pawn away. So we're similar in our state space and we get the same value function. That's our approximation. And this is nice because it approximates to, it generalizes to new states we've never seen. And so in this linear method, if we're doing stochastic gradient descent, right, we want to know what the gradient is of our v hat function. Well, the gradient of our v hat function, right, if we look at any particular weight, the derivative of v hat with respect to the weight is just the associated x, right? Because remember, v hat is equal to the summation from I equals 1 to d of wi xi. So therefore, it's, you know, w1 x1 plus w2 x2 plus wd xd. So therefore, when you take the derivative with respect to any particular weight, it's just going to be the associated x. And so that's the partial derivative. The gradient is just going to be a bunch of x's, right? Because this is equal to x1 of s. This is equal to x2 of s, all the way to xd of s. And that is just equal x of s. Although, since this is a row vector, it's the x of s transposed. So that tells us that if we have a sorry, I'm just thinking about something. So yeah, if we have a the gradient is just our x, and so therefore here we can replace this. This is the same function. This is the same slide we had before as far as finding the individual losses. We're going to place this with x of s. Okay. So what we're basically be doing is saying we are going to take the difference between the predicted and actual value. If that's 0, then we're perfect here and we don't make any changes to the weights. But if we're imperfect, we're then going to multiply that by our x's, and that's going to adjust our weights. So if we have a large x value, that's going to produce an associated large change in the weight. And if we have a small x value, that's going to produce a small change in the weight, right? And notice, again, these are vector addition, because this is a vector and x is a vector. Questions? All right, let me quickly show you a video. This is from a neural network class. So that is not it. One moment. Here we go. So we have some points, right? As you can see here, we're trying to fit a line to these points. And we're going to use gradient descent to do it. I will share this Colab notebook in the schedule as soon as we get done here. So the gradient descent, we can see this here, f of x, whoop, I can't write on here. So f of x minus y, okay? And we have a 2 left here because our original function, our loss function, didn't have a half. So we just had the 2 that came down from the exponent. So that came down here. We are using a a0 plus x times a1. And our weight are basically this a0 and a1, so the intercept and the slope. So what we do for gradient descent is, I have it here in just a second. Oh yeah, we go through and we reduce the w's, basically reduce the a0, we reduce the a1, so reduce those weights. But when we run, here's the key I want to show you. So we start out with a0 and a1 equal to 1. Okay, this a1 apparently looks slightly more than 0, I'm not sure why. But we end up here, and then what we're going through is we take a batch of these and we go ahead and calculate the gradient and we update the w's. And so now you can see from here to here, we update the intercept slightly and the slope a little more. And then we keep updating. And eventually we slow down and converge. So this is an example of the gradient descent. So we're not using a regression function to try and come up with the, this in a closed form. Instead, we're just doing this follow the gradient, taking small steps. Follow the gradient, taking small steps, and so on. Any questions? To give you a preview, by the way, your homework is going to basically be working with this gradient descent. So you are going to be doing one step of the gradient descent. So you'll be given a W with current values. You'll be given an S, and you'll be given a definition for the loss, which is the same definition we have here. And you will just go ahead and update those W values. All right, anything before we call it a day? Right, a reminder that the program assignment 6 is due Friday evening. We will have so we have homework due next week. We'll have one more homework the following week and one more program assignment, and then quizzes, and then a final, and that is it. Next week, we should have on Wednesday, I will confirm a guest lecture and talking about her research on reinforcement learning. So Dr. Tabati. All right, so you can stick around for office hours if you'd like. Otherwise, I will talk to you on Monday. If someone has any particular problems or questions with the program assignments, go ahead and use Piazza as always. If you need to set up office hours with me, feel free to contact me and we can try and do that. Mazda, make sure you don't leave because I need to talk to you about your midterm.